Hello, so this is a video on using sigma notation and together with Riemann sums to represent the area under a curve. So we'll start out with just a normal Riemann sum, like say a right-hand rule. So if you're looking at this picture, we're trying to find the area under this curve. We'll call it f of x. Whoops, f of x from x equals 2 to x equals 7. So the first, and we're going to use, in this case, 1, 2, 3, 4, 5. Let's actually change this to x equals 4. Let's do, yeah, let's go to here. Call this 5. Okay. So we're going to, first of all, we want to know how, if we're going to find the area of the curve, we're going to add up a bunch of rectangles, right? So the first thing we need to know is the width. And of course, the width we've discovered is if you just take the total interval and divide by the number of rectangles. So in this case, this would be 5 minus 2 over the total number of rectangles is 1, 2, 3, 4, 5, 6. So 5 minus 2 is 3, so it'd be 3 over 6, or 1/2. So the width is 1/2. So we would take 1/2 times, and then, remember we're multiplying 1/2 times each of the heights of the rectangles. So if we're going to use a right-hand rule, we would go like this, like this, like this, like this, like that, and like that. Okay? And so the first height of the rectangle would be f of 2.5 because it's half over from 2. And then the next one would be f of 3, and then f of 3.5, f of 4, and f of 4.5 plus f of 5. Let's see, we got 1, 2, 3, 4, 5, 6 rectangles. That's what we should have. Okay, so that would be the right-hand rule. Now what I want to do is to think about this in terms of a Riemann sum. So if we were doing this as a Riemann sum, remember we talked about this at the end of the last video, that the way the Riemann sum works is we're going to take I, which is the indice, and in this case we'll start with 1, and we're going to run it until it, in this case, the last number we'll plug in would be 6, because 1 would give us the first one, 2 would give us the next one, 3, 4, 5, 6. So the last I I'm going to plug in is 6. Now, what are we going to do with this? So we're going to take a 1/2 times something, because it'll always be 1/2 times. And basically what we're going to do is set up a generic version of one of these areas. And so we know that it's 1/2 times f of something, right? So this would be f of, and then the question is, f of what? Well, we know that we're adding 1/2 each time to go from there to there to there, and we have to start at 2. So if we start out with a 2, and then we're just going to add I over 2. So that way, let's see if it works. So if I plug in a 1 in there, that'd be f of 2.5. If I plug a 2 in there, that'd be f of 2 plus 1, which would be 3. If I plug a 3 in for I get f of 2 plus 1.5, which would be 3.5, and notice it works. So that's an example of a Riemann sum using represented with sigma notation. So again, the way sigma notation works is I have an indice that's going to be the variable of the Riemann sum, and I start with 1 or 0. It's works either way. And then the number up here is the last number I plug in for I. So let's say we wanted to do a left Riemann sum. So just to get it started, that of course would be 1/2 times, and the first thing I plug in is 2, isn't it? Plus f of 2.5 plus dot dot dot, and the last thing I plug in would be f of 4.5. So if we want to represent that with a Riemann sum, with sigma notation, I mean. This time, I'm going to start with 0. That way I can use the same formula. Oops. F of 2 plus I over 2. But then the last number I plug in, instead of being 6, would be 5. So notice if I plug 0 in there, I get f of 2. If I plug 5 in there, I get 2 plus 2.5, which would be 4.5. So this gets me through all of them. And now let's do the most challenging one. What if we wanted to do the midpoint formula? So that would be 1/2, of course, still on the outside. And the first thing I'm going to plug in is that middle value right there, right? So that would be 2.25 plus, and then the next one would be that middle value right there, which would be 2.75, etc. So to get the midpoint, and the last thing I'm going to plug in would be f of, and that would be this point right here, which should be 4.75. So if we're going to use that sigma Riemann's or sigma notation to do that, we're going to go, again, this is going to be 1/2, and in this case, I'm going to go, I runs from, now I could start with 0 or 1, doesn't matter. I just got to make sure that the first thing I plug in is going to be the right number, this 2.25. So let's just let I equal, let's let I equal 0. And then we'll have to go to 5. So then here we'll have f of 2.25 plus, now we still want to jump it up by 1/2 each time, right? So we're going to put a plus I over 2. So notice in this case, when I plug in 0, I get the 2.25. When I plug in a 1, I get 2.25 plus 1/2, which would be 2.75. And when I plug the last number in, 5, I get 2.25 plus 2.5, which would be 4.75. So it works. Now, if we were doing all this, let's say we found out later that f of x was equal to sine of x plus 2 or something like that. I know that it doesn't look like that, but let's just say that's what it was. Well, then all it does to my Riemann sum is I'm still going to run I from 0 to 5. It's still going to be 1/2. But instead of this f of, I'm going to have sine of 2.25 plus I over 2 plus 2. So in other words, we're just replacing f with the formula for f. So the key is your sigma notation is figuring out what the indices are, and this is always going to be the width of the rectangle, and then this will be some kind of a formula that produces the height of the rectangle. All right, so hopefully that's helpful. Now the whole purpose of this, of course, is to, what we really want is we want to be able to find the exact area of the curve. And we talked about this a couple of videos ago, that if the more rectangles I take, or the more subintervals I divide it up into, the better the approximation. So when we do sigma notation like this, what we can do is let's let the number of rectangles be n. Number of rectangles be n. So now how does that change things? Well, we go back up to the width, and instead of a 6 here, we have an n here. So that means that my width is going to be 3 over n. So that's one thing that changes. So in my sigma notation, I is going to run, and we'll just do the right-hand rule. So I'm still going to start with 1. Now, in this case, I'm going to go up to n. N number of rectangles, right? And my new 1/2, so the width now is 3 over n, isn't it? So I'm going to put a 3 over n right there. And then on the inside here, I'm going to have f of, well, the 2 is the same, but what I'm adding each time is 3i over n. And again, if my formula was, sine of x plus 2, then this would look like I runs from 1 to n of 3 over n times sine of 2 plus 3i over n plus 2. And that would be my signal notation. Now, what does this do for me? Well, since my number of rectangles is n, then I can get real fancy and throw a limit in front of it and let n approach infinity. So now what we're doing is we're letting the number of rectangles approach infinity, which means each rectangle is going to get smaller and smaller and smaller, because as n gets bigger, right, as n gets bigger, this fraction gets smaller. So the width gets smaller and smaller and smaller. And so the margin of error up here, these little error pockets are going to get smaller and smaller and smaller. And what happens is that this limit is approaching the actual area, the exact area. So that's why we want to be able to write this in terms of signal notation. So there's a worksheet for you to work on now that'll practice, see if you got this idea of signal notation. We're not going to spend a lot of time on this, but it is worthwhile to play around with this, especially if you're going on to Calc 3, because we do signal notation a bunch in there. So, all right. Hope you enjoyed this.